Okay, so we just got done with section 7.5, and in 7.6 is really 7.5, but it's just all in the computer and the calculator and stuff like that. Like there's a lot of technology involved with those problems. It's all technology, really. Because of time, we're not going to do section 7.6. 7.7, I'm going to leave as an extra credit opportunity for you guys. I'll talk about that in class. It's on approximate integration. Okay, so here's a worksheet that I'll have you do there for extra credit, and so that's 7.7. Okay, 7.8 is the next section, and that's the last section in chapter 7. Also, by the way. Exam 2 is going to cover 7.8, 8.1, 8.2, and 8.3. Okay, there's an 8.4 and 8.5, but because of time, we're not going to do those also. 7.8 is called improper integrals. Okay, and an improper integral is an integral including an infinite interval or an infinite discontinuity. Okay, like a vertical asymptote or something like that. So just as an example here, to get us started, suppose that I want to find the area under the curve of 1 over x squared going from 1 to t. Okay, so I drew that out. Here's 1 over x squared, and here's 1, and I'm going to some spot on the x-axis, so I'll call that t. Then the area will be in, where I want to integrate 1 over x squared going from 1 to t, and the antiderivative of x to the negative second is x to the negative first divided by negative 1, or negative 1 over x. I'm evaluating that from 1 to t, and when I plug in my bounds there, I got negative 1 over t minus a negative 1, so that's 1 minus 1 over t. Okay, that'd be just the formula that I could use to get the area of this region here that I got shaded in. Now, you would guess that as t approaches infinity, you have an infinite area, right? Because the curve is never going to get to the x-axis. Well, if we look at this through a limit, the limit as t approaches infinity of a of t is what I'm calling this area here. Here's the formula for getting the area. It's 1 minus 1 over t. And when I compute that limit, the limit as t approaches infinity of 1 over t, that's 0, right? Because the denominator is me growing without a bound, as the numerator just sits at 1. And limit of constants is always the constant, so I get 1. Okay, so the area is approaching 1 as t is approaching infinity. Now this is an example of an improper integral. Okay, notation that we're going to use here. So, this was the integral I was computing. I'm going from 1 to infinity. You find the area under the curve of 1 over x squared dx. And now an infinite interval always needs to be converted to a limit. Always. Do not make the mistake and don't do that. Okay, you'll lose points for bad notation with this section here. So it's going to be the limit as t approaches infinity of the integral going from 1 to t of 1 over x squared dx, and that limit is 1. Okay, so this is the type 1 kind of improper integral. There's a type 1 and type 2 kind. Okay, this is the type 1 kind. The type 1 kind of improper integral is called infinite intervals. So if I, want to find the area of a region that's an infinite region. There's 3 kinds of infinite intervals there. So if f is continuous, f is a function on an interval going from a to infinity, like 1 to infinity, okay? Then if we want to integrate this function on the interval a to infinity, it has to be converted to a limit. It has to be converted to a limit. It has to be converted to a limit. Do not make the mistake and don't write any limit notation down. You will lose points for that. So you're going to have the limit as b approaches infinity. B is, just another constant there, going of the integral going from a to b of f of x dx. If you have a continuous function on an interval going from negative infinity to b, including b there, then you're going to replace the lower bound with a. So you got the limit as a approaches negative infinity of the integral going from a to b of f of x dx. And if you got a continuous function on the entire number line, then you want to integrate that function, or the area underneath the curve. So the area under the curve going from negative infinity to infinity is, you select a spot, just a number c, and c is going to be, a number that you're going to have to come up with on your own, and it will be an obvious number there. We'll look at some examples of that. But you'll split it at c, and you'll find the area under the curve going from negative infinity to c of f of x dx, and then add the rest of the area under the curve going from c to infinity of f of x dx. Okay? These integrals, so the integral going from a to infinity of f of x dx and the integral going from negative infinity to b of f of x dx are called convergent if the limit exists. Convergent is going to be a very important word for us later on when we get to chapter 11. We're going to see that word all over the place there. So convergence just means that the area exists. Okay? And you got a divergent integral if the limit does not exist. Okay, now in this definition here, I'm using the word limit. Okay? So whenever the point of this is to say that whenever you're integrating an improper integral, improper integrals always need to be looked at in terms of limits. Always. Okay? So that's why, I kind of mentioned the notation there again. If we look at this example, okay, suppose that we want to find the area under the curve of 1 over x going from 1 to infinity. Up here, I was looking at the area under the curve going from 1 to infinity of 1 over x squared. Okay? So, well, this is an improper integral. So the first thing is I have to write this down in terms of limits. I'm going to say the limit as t approaches infinity of the integral going from 1 to t of 1 over x dx. And the antiderivative of 1 over x is the ln of the absolute value of t. I'm going from 1 to t. And then when I plug in my bounds here, sorry, this should be an x, ln of x. So then when I plug in my bounds, I got the ln of t minus the ln of 1. And t is approaching infinity. Okay, the ln of 1 is 0. The ln of infinity is infinity. So the answer would be infinity. Okay, now, so what we see here is that the integral going from 1 to infinity of 1 over x squared dx converges, right? That was 1 that we saw up here. And the integral going from 1 to infinity of 1 over x dx diverges, right? Because we're getting infinity there. So what that tells us is that, when we look at these two areas under the curve, now the curves look very similar, but the area under this curve, y equals 1 over x squared, is a finite area. The area under this curve, y equals 1 over x, is an infinite area. Okay, again, these two curves look very similar to each other, but geometrically, the curves look similar for when x is bigger than 1, but 1 over x squared is going to approach 0 faster than 1 over x. Okay, so because that happens, where you're approaching 0 faster than 1 over x, you're going to have a finite area there. Okay. let's take a look at this next example. It says, for what values of p is the integral going from 1 to infinity of 1 over x to the p dx convergent? Okay, well, we just saw that if p is 1, we got infinity, right? So that would mean that we got a divergent integral. And if p is 2, we got a convergent integral. Okay, so like what are all the values of p that make this integral here convergent? Well, so if we integrate this this function, again, I've got an improper integral, so the first thing that I'm going to do is use the limit definition. That is always going to be the first thing that I do. So it's going to be the limit as t approaches infinity of the integral going from 1 to t of 1 over x to the p dx. 1 over x to the p, that's the same as x to the negative p. Okay, so then when I find the antiderivative, add 1 to the power divided by the new power. So I got x to the negative p plus 1 divided by negative p plus 1. I'm taking the limit as t approaches infinity of that. And I'm going from 1 to t. So then when I plug in my bounds here, plug in t first, and 1 over 1 minus p, that's a constant. I can bring that outside. I can actually bring that outside the limit notation if I want to, because the limit is in terms of t. Anything involving t has to stay inside the limit, of course. So then when I plug in the upper bound, t, I got t to the 1 minus p minus 1 to any power is always 1. Okay, so here's where I'm at right now. Now the next thing that I do is I got the limit as t approaches infinity of 1 over 1 minus p times t to the 1 minus p. That's the same thing as 1 over t to the p minus 1. In other words, a to the power x, we'll call it, is the same as 1 over a to the power negative x. So all I'm doing here is I'm using that rule, and I'm you know, with the power, I'm multiplying it by negative 1. So negative 1 plus p, that's the same as p minus 1. Okay. Now, the reason I did that is because it's easier for me to compute this limit here. Okay. For example, if p is big, some number bigger than 1, like if p is 2, then I got 1 divided by p is 2, so 1 divided by t is going to approach 0, right? Because the denominator is growing without a bound as the numerator just sits at 1. All these numbers are constants, right? And so if p is some number less than 1, then t to the 1 minus p, okay, like if p is, 1/2, I got t to the 1/2 power, the square root of t. The limit as t approaches infinity of the square root of t, that'd be infinity. Okay, so the point with that is to say that you're going to have a convergent integral for this guy here as long as p is some number that is bigger than 1, right? If p is 1, then you got a divergent integral. If p is some number less than 1, you've also got a divergent integral. If p is convergent, then this term goes to 0, right? So you got negative 1 divided by 1 minus p. That's the same as 1 divided by p minus 1 is going to be the answer, as long as p is some number bigger than 1. Okay? Now, you're going to need to know this for when we get into chapter 11. Okay? And in every single section in chapter 11, they're going to talk about convergent series and divergent series. Okay? Which is very similar to what we're looking at here with convergent and divergent integrals. And there's different tests that we're going to need to know, okay? One of them is called the P-series test. Okay, well, that's very, very much related to what we just did here, okay? So in the P-series test, you're going to have a convergent P-series, is what it's called, as long as P is a number that's bigger than 1, and you're going to have a divergent P-series as long as P is a number that's less than or equal to 1. Okay, again, more on that later once we get into chapter 11. But again, the point is to say that convergent and divergent definitions, those are going to be very important. So this section is really kind of the first place where we're seeing that. So a convergent integral, again, just means that the limit exists, and a divergent integral means that the limit does not exist, or it's infinity or negative infinity. Some item that's not a real number there. Okay, we'll go ahead and stop the video right here, and I'll pick up with this example in the next video.